And the reason it's being compressed is because all of the other air molecules, all the parcels of air are being forced down upon it. We're in a high pressure area, the air is being forced down. So where this lump of air previously could hold all of these air molecules, this air that's now being forced under pressure, what happens when you compress something? Clues in the name, it gets smaller. Is that smaller? And so rather than having, I'll say 9, we can now only fit in, well, this 9 is being compressed. So within the same parcel of air, that air is being put under more pressure, making the air more dense. If this air, that we're in a low pressure area, the air beneath it is allowed to expand, making it larger. And therefore these air molecules have got more area for it to move around, so this is now less dense. It's very, very simple. So higher pressure, I've done way too many molecules in there, that lump of air is under pressure and forced into a gap, whereas there is less pressure, the air is now allowed to expand. And it's the same when we're referring to temperature. Oh, lost a paraglider.
Try your reserve.
Because when we cool something down, it shrinks. Normally the case, most cases. And so this parcel of air with a lower temperature gets smaller in size. And so those molecules of air are compressed more tightly together, making the air more dense. And again, if we were to heat this parcel of air, it makes it larger, meaning those molecules of air have got more space around, making the air less dense. Now, this brings us into two contrasting facts. So, we got a, do us a favour, just wet that one up for me. The issue that we have is that we have a pressure and temperature fighting against each other. So, as we know, as we start to climb, thanks Barry, sorry I ran out of. If this is ground level, and this being altitude, we know that the temperature, we'll call it at surface, call it 15 degrees, as we gain with height, it becomes colder. So 15, 14, 13, 12, 11, 10, we'll call it 6. So in theory, this parcel of air that was down here, as it starts to rise, is getting colder, so therefore should compress. But the issue being that as we also climb, there is a reduction in pressure. Which means that that lump of air will be bigger. And so we have two contrasting issues. The cold air says it should be more dense, but the less pressure says it should be less dense. Pressure has an overriding factor over temperature. The change in pressure will affect the density more than temperature. So really when we're looking at temperature, yes, we are looking at the climb rate and things, but when we're looking specifically on how well an aerofoil will travel through the air, the pressure is going to affect the density more. If we're looking at the performance of our aircraft on the ground, temperature becomes a factor. And vice versa, should this be warmer, the air is less dense, and therefore the aircraft is going to be perform less. Less air molecules are going into an engine. Now, what I also want to bring into play is what Andy was saying about humidity, and this is a huge factor and something that a lot of people get wrong. It's referring to relative humidity and humidity, and we do get a figure for this, and it's certainly worth bearing in mind. But 80% humidity on one day isn't the same as 80% humidity on another. So, coming back to this parcel of air, the ISA figures that we are given assumes dry air. So if we have a parcel of air here now that should be holding 9 molecules of air, if it has water in it, it can hold less molecules of air because it's taken up by water. So the humidity will affect the density of the air. Now, we mentioned this, a cold lump of air can hold less water than a warm lump of air. So let's just say that this one can hold 20 millilitres of water. Once there is 20 millilitres of water in this parcel of air, it's reached its maximum. It will become 100% humid. Yeah, so 100%, the relative humidity will be 100%. But let's say that this parcel of air can hold 40 millilitres of water before it reaches 100% humidity. But you can see that the figure that we're given, the relative humidity, will still be 50%. But in this scenario, there is only 10 millilitres of water, where in this scenario, there is 20 millilitres of water. So relative humidity makes a huge difference depending on the parcel of air in which it's actually contained in. Now, we'll come back to this one in a second. This comes into play depending on where the air mass is coming from. Should it be coming from the tropical regions, it's going to be a warm air mass. Should it be coming from the polar regions, it's going to be a cold air mass. So, for me, when I'm looking at particularly forecasting, when we're in our winter months, I don't particularly look too far than a couple of days. But when we're in the summer months, I'm looking more 4, 5, 6 days in advance, because it's a bit more predictable. And again, we'll come on to that in another one. So relative humidity for us is quite important, because from it we can work out quite important things, or guess particularly on what cloud base is going to be like. So we've already discussed that with temperature and with altitude, that air is going to start to compress with temperature. So let's say that at ground level, this lump of air, what would we say that is? There is 25% humidity. And let's put this at ground level. So at ground level. Now, we're assuming this parcel of air is being forced to rise. So this parcel of air now rises, and as we have the change in temperature, that parcel of air gets smaller. But the water content remains the same. So let's say it's 25% humidity. Let's say there's 10 millilitres of water in this. that parcel of air gets smaller, the water content stays the same. And so it becomes 50% water. It's the same amount of water, but because that parcel of air is being compressed, it's now a smaller vessel, making the air less dense. If that air continues to rise, that parcel of air gets even smaller, to the point where that 10 millilitres of water will reach 100% humidity. It's all holds as much water as that possibly can hold, just like a sponge. So if you dip a sponge into a bucket and bring it out and slowly start compress it, it's like that parcel of air. At some point, that water is going to come out of the sponge and start falling. Now, this is not where I'm saying that's how it now rains, but should this air continue to cool anymore, that this is where the air becomes fully saturated and starts to form clouds. Now, there is a figure that's given on this, and it's called dew point. Dew point is a very important thing to bear in mind. Certainly around sort of winter months, you can really aid your guessing on A, whether it's going to be foggy, and B, what cloud base is going to be. So let's say that the temperature here, we'll keep it simple, is 15 degrees C. And they give you a dew point temperature of 9 degrees. Now, assuming, and there is a better figure than this, but assuming that we're therefore talking about air that's forced to rise, this is where we would follow the DALR lapse rate of 3 degrees, cooling of 3 degrees per 1,000 feet. So at 1,000 feet, the temperature in this scenario in rising air will be 12 degrees. At the next temperature, the next 1,000 feet, it's going to be 9 degrees. They've already told us that dew point is 9 degrees. So based on the DLAR of 3 degrees, we know that cloud base is going to be 2,000 feet. Very useful to know should be you planning across country where terrain is slightly higher than 2,000 feet. Now, the thing that we want to be looking at, particularly on a forecast, is where you'll get the figure. I can show you, I've grabbed this from the very first one. You'll see that on the, where's the TAF and the METAR. You can see here, we've got all of this information for EGNX, which is East Midlands, the date and the time that it was forecast, the wind speed, CAV OK, one that everyone gets wrong, ceiling and visibility OK. But you can see here there's an 11, that's the surface temperature. And the next one here, M03, dew point is -3. So from this we can work out, based on a lapse rate of 3 degrees, because obviously moisture, we need moisture to form clouds, meaning that we can work out what the cloud base is based on the temperature shared into 3, and we can get our altitude. The figures that we are looking for is when we start getting the relative humidity on a forecast, and they might say that relative humidity is 80%. So if we see a relative humidity of 80%, and we see a surface temperature of, say, 1 degree, so we're assuming it's winter, and then you get a dew point of -1, we can pretty much assume that it's going to be foggy. The air mass is pretty much fully saturated already, before it's gone anywhere. 80%. And it's saying that the temperature is 1 degree, it's only got to cool by 2 degrees before that parcel of air becomes fully saturated. Therefore, cloud base is going to be really, really low. So yeah, one of the things that a lot of people get confused with relative humidity. Now, this brings us on to that air mass. And so we've looked at synoptic charts and we've been able to work out where the air is coming from, as in the northeast. But what does that mean to us? And again, we're a UK flying school, so sorry to those in South Africa. We often get asked the question on why is the English weather so bad? Well, to be honest, it's not our fault. We just happen to live in a very unique place on the planet. So let's put on our...
We have weather, everybody else has a climate.
That's right, that's just, yeah. So here we go, let's put on... Are we happy with that's UK? I'm not an R5 very well, it's jelly bean. It's a bit of Ireland here.
What happens to Wales, dude?
It's there. And then we know that we've got some other land that's here. When we're looking at a synoptic chart, we're not just looking at what the wind's coming, we're looking at that parcel of air and how that is affected. Now, one of the reasons why that we have such bad weather is because that the tropical region cuts through about there. So here is the tropical region, and therefore this is the polar region. And the other issue that we have is everything this way is sea, and everything this way is land. So that again brings us into a nice divide. Very easily now we've got tropical and polar regions, and we have maritime and continental. So 4 distinct zones. Now, our prevailing winds will come from one of these regions. When it's travelling from this way, it's known as a continental or tropical continental. And this means that it's travelling over land. It's going to be dry air and it's going to be warm. So there's going to be very little moisture in the air, but it's going to be a larger parcel of air. So pressure obviously is affected. That lump of air is different. Whereas when the air mass is coming from this direction, we still have a tropical region, but now it's maritime. So that, let's put this parcel of air, so the parcel of air on this one is going to be dry and a big parcel of air. Parcel of air coming from this way, it's going to be wet, but it's also going to be warm. So that parcel of air is going to be, I hate these pens. This parcel of air is going to be warm, but there's going to be water in it. When we're talking about an air mass that's coming from the northeast, east from the east, we know it's going to be cold, but it's going to be dry. So that parcel of air is going to be, I don't know, the same size, isn't it? There we go. Closely packed together, so it's going to be more dense, but it's going to be dry. Whereas air that's coming from this region is going to be polar, so it's going to be a smaller parcel of air, and it's also going to have water in it. So, same amount of water, but the parcel of air in which it's in, it can't hold as much. And so, from this we can follow the base model. Air that's coming in this way, it's got to contain a lot of water before it starts to, say, rain or bring in a large amount of clouds. What we tend to get from air mass that's coming from this way tends to be poor visibility, relatively to light, strong winds, but it's going to be a larger air mass. So temperature is going to be slightly higher, pressure is going to be slightly lower, and again, any moisture that's in there is going to bring more like drizzle type rain. When we're looking at air that's coming from the polar continental, again it's going to be dry air, so it's very unlikely are we going to get storms, but there's very little for it to come through, so it's going to be stronger winds pretty much rattles straight through. We call it our northeast thing. Well, coming from this direction, a dry parcel of air, so very little storms or showers, with a high pressure. When we're looking at air that's coming in from the polar regions, it's going to be cold with a lot of moisture in it, meaning that it's not going to be, it's probably going to be quite stormy weather, but it's not going to be like sheet rain, it's going to be showers. Doesn't take much for this water that's in that parcel of air to reach 100% humidity and lose all of its moisture, so you tend to get a lot more showery based weather that's travelling in from there. So understanding where the air is coming from really will aid you in your forecasting, particularly when you're seeing winds coming in. And you can also get things like returning polar maritimes, where the key source is going to be a low pressure system that's here, and as it's rattling around, what it'll do is it'll slowly come into this tropical continental. It's pretty much a good description of a depression, and this air travelling around it temporarily falls in to this tropical continental, and it changes the characteristics and draws it in. So its key source is here, but because that depression is bringing it through. So really looking at that synoptic chart and going, what's that parcel of air being affected by? Where is it coming from? Understanding its key source and its key location. Okay, so source points. What time are we on? Right, okay. We could talk about MET forever, but what I want you to do is really just think of that parcel of air and how it's being affected by the conditions that it's under. Now, I'm aware we've only sort of got 15, 16 minutes left. And again, people have been drumming us into nav. So I'll scoot on and we'll talk a little bit about navigation. Now, navigation for me is all about flight planning. If you get as much information done on the ground as you possibly can, and again, as experience comes in, you will kind of do less and less because you won't need as much information. It's pointless circling that reservoir that you've flown over 1,000 times. You might become aware of a radio frequency that you use all the time. So things do become, second nature. It's like we go into a roundabout. I mean, the first time you came to a roundabout learning to drive, it was like, oh God, there's a roundabout. Now, we just take the roundabout. Same as changing gear. So there's a lot of things that come in. What I want to spend some time with you about, if I can find my notes, is aiding on that flight planning. And what I want to do really, particularly for you guys that are doing exams or about to take exams or thinking about, is give you ways to practice, because you don't want to walk into any exam really hoping that you're going to remember. And navigation is a real tough one, because in order to answer one question, you must call upon 5 or 6 different pieces of information to give one answer. In fact, nav probably is one of the more difficult ones, because you're asked questions that aren't even give you any marks. Now find your airfields. It just sounds simple. And the one thing that a lot of people get wrong is the 1 in 60 rule. So 1 in 60. Now, why do you need to learn the 1 in 60 rule? You might get a question on it in your exam. This comes back to the days where they were flying multi-crews and you had the captain and the first officer flying a great big bomber, and behind them there was a navigator, and the co-pilot or pilot would say, we're approaching a reservoir. And that was, oh, hang on, that reservoir shouldn't be on the nose, it should be off there to the right. So this isn't necessarily being lost. This is knowing where you are, just knowing that you aren't where you should be. Does that make sense? So the issue being is that we are here, we're trying to travel to there, and we know that we are here. We know we are here because there might be a lake. So we're not completely lost, but we shouldn't be over that lake. It should be on our, well, if this is direction of travel, it should be on our left-hand side. So this is where the 1 in 60 rule comes into place. And the 1 in 60 rule is a basic equation saying for every 1 nautical mile you are off track, for every 60 miles you're 1 degree off track. Which means we can use, I say this painfully because I know you, that we can use a simple equation. I'm trying my hardest to keep a straight face. And the simple equation, and again, don't practice this with the equation in front of you. Practice it until you're doing it and then turn the equation over. And then practice it again. So the first thing we need to do is DOT, distance off track. Put that in brackets. And then we times that by 60. Back to the old algebra days, anything in brackets you do first, anything next to each other you times by. If you have a line, you then divide it. So the next one that we're doing is distance gone. So this is my way of practicing it. And you can invent figures to do this all by your own. We're travelling from A to B. Put a dot somewhere on that track. For this instance, keep it in the first half. And now we need to give a distance. So this total track, we'll say, for keeping figures easy, is 100 nautical miles. So based on this, distance off track, first of all, let's say we are 4 nautical miles off track. So distance off track is 4. Times that by 60 gives us 240. 240. Next thing we're doing is distance gone. So this is where we are. So if that's 100 miles, that must be 50. We'll call that 40. So 240 shared into 40. 16. Why can't I work 240 shared into 40?
6.
6 degrees. Thanks, Barry. You may need to be on calculator duty. So you're doing this in my head in the flex wing. It says that we are 6 degrees. Now this is assuming that we've done this track, we've done the equation in our head, we haven't gone past 50 degrees. 6 degrees will put us on a parallel track. So we need to times this answer by 2. So 12 degrees will turn us back onto a heading to pick up our track within the same distance. Simple enough? So the practice, draw a line, put a dot on it, and then practice this equation. I will give you some hints as well. The other scenario is that should we have gone past halfway, say we are now here, if we take this track, work this equation, we will have missed our destination by following this equation. And so therefore we need to complicate the equation even more. And so this is where we then do a second figure, which is total track required shared into distance to go. Now again, do the brackets first, times, divide, and then times these together because they're next to each other. So a simple equation, let's work this one out. So A travelling to B. Let's put a distance on it again, keep it 100 miles to make my life easier. Put a dot on it, that's where we are. So first of all we're going to do our distance off track. So if this is 100 miles, we'll assume that this is, I might as well use 4 again. So distance off track is 4 nautical miles times by 60 equals 240 shared into distance gone. So if that's 50, 60, call that 70. Got your calculator, Barry? Shared into 70.
33.
I'm at 7.3.
33.
33?
Yeah, 3.3.
3.3, okay. 3.3 degrees. Now we know that that will put us on a parallel track. So this is where we need to use the second part of the equation. Total track required is 100 miles. Shared into distance to go. Well, if we've done 70, therefore we need to do a remaining 30.
It's actually 3.4.
As someone mentioned, there we go. So 100 shared into 30 is again 3.3.
3.3.
3.3. Times those together, so 3 times 3 is 9.
Aye.
9 point, well, we'll call it 9.
About 11.
How many?
About 11ish.
11?
That's close. Yeah.
3 threes?
3.3 times 3.4.
9? 3 threes, 3.
3 threes are 9.
3 point. I'm just going to put 9. I'm just going to assume that. So
It's 11.
9.9 degrees. This means that when we get to this point, we follow this simple equation, which you can see is really easy. We alter our heading by 9.9 degrees, and that will take us direct to our destination. Practice both, because on your exam, they will ask you to either regain track or fly direct to the destination. If the question is worded fly direct to the destination, it doesn't really matter where you are. But if they ask you to regain track, the chances are that you're not going to be halfway and therefore only need to do half of the equation. So get used to this figure, and then once you've done your exam, you can choose to ignore it. So that's the theory side of it. What do we actually use in a practical sense? And this is something that I used for quite some time. It was my comfort blanket. And this is the 10-degree method. I've done it in red for a reason, because that's what I used to do. And again, we're going to assume we are travelling from A to B. There's good cake at B, and that's the only reason we fly. On each one of your track lines, you draw a 10-degree line either side of your track from each one. And then you would you could possibly even put in a 5-degree line. Again, the downside on this was it would clutter your map. But I knew that if I found myself, say, here, that I was 5 degrees from my departure. It also meant that I was, what would this be? 3 degrees off my destination. Add them together. Alter your heading by 8 degrees. And you'll fly straight to your destination. That's why I used to use that one, because it was easy. Even I can do simple addition. With the fan lines or the 10-degree lines, you know, because you've already marked, that it is 10 degrees. And a simple, well, I'm about, rule of thumb, I'm about a few degrees off there. And I'm this, it was easy to sight, particularly in a flex wing on a map. So yes, the 10-degree method was something that I actually used. The 1 in 60 degree method, it will help you pass your exam. You are going to get a question on it. As eggs are eggs, they don't just throw it in there for a reason. But the 10-degree method really did help me on navigation, and certainly avoid me wandering too far off track. If we hit 10 degrees, then I knew it was easy enough for me to get back. Okay. we can go into more loss procedure, and we can certainly go into more meteorology on another day. The loss procedure follows a very, very simple rule. And this is where carrying out some form of timepiece or marking your time and marking your map. When you see something obvious, I definitely saw that airfield at this time. You know, if I was flying along on a typical route and I saw an airfield here and I'd taken off at 11 and it took me 20 minutes to get there, I would mark that with a 20. So that I definitely knew that that airfield was there at 20 minutes. So should I therefore not have found my destination or have no point of reference, I knew that I saw that at 20 minutes past. You'll be surprised on when you're lost on how time seems to go so quickly. It may only be 25 past. But because you haven't seen anything, it feels like you've gone forever, and then your mind takes over. We'll come on to human performance limitations, definitely a very important subject. But being aware of the time really, really makes a difference. And so what you need to be aware is that before you're lost, you're temporarily unaware of your location. And I would say that this will be between 5 to 10 mins after you last saw something that you definitely recognised. Now the key thing is to try and find some point of reference. This is where you would do ground to map, map to ground, and try and see something. What you don't want to start doing is start turning the plane. Look with your head, keep the track, check your compass, make sure that you're flying the compass, the heading that you've decided. Make a note. Were you expecting to pass this at 15 minutes past? Therefore, if you had a tailwind, and this way you can set up a field of uncertainty. If you know that the wind was coming from this direction, and you should have hit this at 15, but you've hit it at 20, the wind isn't blowing as strong as it's forecast. It's taking you longer to get there, so therefore you're not minimising the tailwind. So if you set up for flying this angle, nose into wind, but the wind's not pushing you, the chances are that you're going to be this side of track. And so you can set up that field of uncertainty and look for things on your map. Rather than trying to find anything, you're now pretty sure you're in that area somewhere. It's only when you go into fully lost, and I would say that this would be 10 to 20 minutes after I definitely saw something that I recognised. We'll come on to the loss procedure because I've just seen the time on how I would resolve that. But first of all, don't panic. Assess the wind, assess your ground speed, assess your compass heading, and look for that field of uncertainty, because the chances are you've just drifted off track, and it won't be by very much. Keep your head up, get your head out of your flight planning software. Everything you need to see is out there. We definitely will come back and talk more about the loss procedure. Anyway, I'm 1 minute over. Normally I'm quite good on time, but I say thank you for everybody watching. I hope that I've stimulated you to understand more about that parcel of air and how it's affected by where it's coming from. Can't wait myself to look forward to Judy's lecture on Sunday. That will be the next time that we are live. We also have a number of other speakers that are coming in. Will's going to come back on as well. And we've started to pre-record some videos as well, which will be on our Facebook and links to our YouTube channel. Let us know what you want. We're open. We've got another 3 weeks to play. So yes, I've seen things about how to rig and de-rig a flex wing. So yeah, that's definitely one that we will do. And again, you know, if you're interested in some pre-recorded videos that you can watch at your leisure, give us a shout. We certainly love your comments and your feedback. But I'm going to say goodbye. Do you want to come back on, Andy?
No.
Brilliant.
Sure. Stay safe, stay well, stay at home.
Brilliant. Thanks, guys. See you soon.